Hello, everybody. Welcome to another episode of Undercooled, a materials education podcast. We are joined by another guest today. We have been trying for a very long time to make this particular interview work, so it's great to finally have Professor Alan Taub on the show. Alan, welcome to the podcast.
Oh, really glad that we finally made this happen. Looking forward to it.
So we always ask the same question at the beginning. Can you tell us a little bit about who you are? How you got into material science, and what was the arc of your career? Because a lot of the students love hearing these stories.
Yeah, well, I started at a very early age knowing I was going to be an engineer. In fact, born and bred in New York City, which had 4 specialty high schools. Some people may know the Arts and Design School from the movie Fame. Well, I went to Brooklyn Technical High School, which was the pre-engineering high school. And interestingly enough, we actually had, I still have it, I don't refer to it anymore. We had a book, we had a course on materials and processes. In high school. That I just found fascinating and probably set my agenda to be a materials scientist and researcher later. What's interesting, the book was written in 1952. I took a look again this morning. 100 pages on wood, 200 pages on metals, and 30 pages on polymers and other materials. So, but I can't say I could truly trace it back to that, but I'm sure that inspired me. So when I went to college, I went to Brown University and got a bachelor's in materials engineering. And then went to Harvard for graduate school. And, Harvard's sort of unique. At the time, they wouldn't call it engineering, so it was the Division of Applied Physics. After that, by the way, my intention was to be a college professor. Probably because I went to 2 Ivy League institutions that there were only a few faculty that had any industrial experience. And I wanted to be one of those. So I went to spend my 5 years in industry so I would be the well-founded professor. That turned into over 30 years. So I started at GE's corporate lab and did work on everything from high temperature materials, actually started on amorphous metals for transformers, which was my thesis. Then got into superconductivity. And something I still have on my desk here at the university, it was the world's first superconducting, conduction-cooled refrigerated magnet, which was a proof point that later became conduction-cooled MRI magnets. Then got tricked into my first leadership role, at which point my goal of being an individual contributor and a professor got sidelined by a move into management. By the way, for those of you who are out there, and I'll touch on it later, you really get that notch in your belt about engineering and research achievement before you move into management. When they first asked me to do it, I said, if you make me do it, I'm going to quit. But they, over time, maneuvered me into my first position, found that I loved it. So I moved into managing the superconducting group, which was interesting. We were working on the superconductors for MRI magnets just in time for the high temperature superconductors to be invented. So that was really a challenge.
Did you go to the Woodstock of Physics?
No, but half my staff did. So
I was at that meeting.
Oh, are you?
Yeah, because I had just gotten a job at Bell Labs, and I was giving a talk there, not on superconductivity, but it was crazy.
I was at one of those meetings, not on superconductivity, but on amorphous metals. where Linus Pauling and John Kahn were having a public debate on whether it was nanocrystalline or amorphous. And yeah, I mean, I was a brand new minted researcher. That was impressive. By the way, if you ever get an opportunity to go to meetings, make sure you go to those special sessions. They're enlightening, and when you realize that the experts are never sure. They're sure of themselves.
Right.
But how often the debate is intense and sometimes in public. It's a lot of fun to watch.
I saw Linus Pauling at the MRS right after cold fusion hit. I don't know if you saw that. It was a huge room because everyone wanted to see Linus Pauling. And he sat there and said, "This whole thing has really bothered me." He said, "I couldn't sleep all night last night because I wasn't sure what I was going to say today. So I reached over and picked up a copy of my book. And I started reading. And after about 45 minutes, I was okay. I put my book down and I could go to sleep. Because it's all, and this is not an explicit podcast, so I can't say the word, but he said it in front of 400 people. It's all crap. And he explained why. And it was great.
Well, I have a slightly different story, which I've been gone now long enough I can talk about. I was at GE leading the materials lab. Cold fusion announcement. And for those of you who don't know, GE is one of the largest turbine producers, both for land-based electrical and clearly for aerospace. Announcement comes out. We made a deal where I was able to put 3 of our key researchers in their lab. Took us about
Fleischmann's lab.
Yeah, took us about 2 weeks for them to come back and say this isn't real, but the implications were big enough that when a breakthrough gets announced, you have to do your due diligence. Despite what we believe and I'm an applied physicist, despite what we think the physics says, you can always get surprised, right?
Fleischmann was a famous guy. You know, he discovered the surface-enhanced Raman stuff. And
well, my assessment, this was not intentional fraud. This was just very subtle experiments which could be misinterpreted, right? Yeah. So then back to my career. So, I was leading the materials lab after the superconductor, director of the lab. When I realized that, I had now spent almost 15 years in one spot. So within GE, I was exploring moving into one of the businesses and that I had done research with. GE was a conglomerate, so, it meant moving, right? So then while I was at it, I get a call from Ford. Would I consider, going over and leading the materials group at Ford? My initial reaction, I have to be honest, was Ford has a research lab. I didn't. I didn't know, right? I knew GMs, right? And go in there. It was a building had just been redone, and so I was actually the first occupant of the new wing.
But it came after Willow Run Labs was really the precursor of the Ford Labs, wasn't it?
I think it started there, moved to Willow Run, and then came back.
Because that was
I'm actually
pretty
not
famous.
Sure. Yeah. It wasn't one of the largest labs.
It wasn't.
It wasn't. By the way, I'm all for it. It's part of my, what I'm proud of having been in. But I realized after a few years there, I had, materials is materials. I had, different attributes, different metrics in the automotive industry. I'd been more aerospace and medical. But then I realized I was really sort of doing the same role of leading a materials lab in an OEM. So I remember I'd only been there like 2 years, going to see Bill Powers, our vice president, and I remember the conversation, right, because you rehearse it. I know I've only been here a while, but I think I'd really like to try engineering. And he started smiling and almost laughing, at which point I couldn't interpret it. And he goes, "Well, we're glad you feel that way. We came to that decision about 6 months ago." So I must have been sending the signals. So actually, my first engineering assignment was crash engineering. Now here's someone who had spent his entire career in R&D. And all of a sudden, I'm responsible for signing off every vehicle of Ford globally. It's meeting its crash requirements. I have to say it was one of the most challenging, but probably almost one of the most satisfying jobs I've had. Number one, I was learning every day because I didn't know much about crash. And it was also at the time when NHTSA introduced the star rating. You know, you go to a vehicle, they had just been introduced. In order to sell a vehicle, there was the legal requirement, well below the star. You could basically sell a vehicle somewhere between 2 and 3 stars. It turns out Ford's internal requirement was mid 4-star. And so, you know, we got the directive, pushed the vehicles to 5-star. I'm really proud to say during that short time frame, we produced more 5-star vehicles than the rest of the industry combined. And it turns out I inherited a group that was both the experimentalists doing the crash testing and the modelers. So it was, and at those times, those models, it was groups of PhDs modeling. You know, today, bachelors can run it. We reduced the number of prototypes, and it was a really great experience to engineering. I was having the time of my life. I get the call, it's time to move. So I was actually given a new vehicle program. Never done a vehicle program. I had done, led research on brakes and on, various materials, but it turned out it was going to be the first high-volume aluminum vehicle in Ford. And learned a lot. I mean, it really changed me. In a way, I would have people from the research, for those of you who are going to experience this, particularly if you're on the research side, either in the corporate lab or the university, it's hard to understand why your breakthrough invention doesn't get commercialized right away. And after about a year in that program where you're deciding which new technologies are going on, I was getting accused by my former colleagues of having moved over to the dark side because I was saying, no, your technology is not ready. It costs too much. It doesn't fit our vehicle brand. And in the middle of that program, I had actually already decided this was great. I'm learning a lot, but I really want to go back to R&D. I knew in my heart I was more sad. I wish I had stayed long enough to get that vehicle through, but I knew that in my heart I had more satisfaction of one technology across the fleet than launching a single vehicle, even though I wish I had done it. But in the midst of that, GM called, would I be willing to run R&D at GM? I jumped and really had a great time there.
How long was it from when Ford began the program for aluminum vehicles, because it was before you joined that group, till it actually did it?
Well, you have to recognize that the aluminum intensive vehicle program, which I helped lead when I got there in research, had been launched before I got there.
Right.
Probably a few years before, we did the prototype aluminum Taurus while I was there. And we also bought Jaguar.
Okay.
And Jaguar and Land Rover made aluminum vehicles. So learned a little bit through that. You started in introducing any new material into an existing product, particularly in a world where it's really run by mechanical and electrical engineers and now software engineers, but let's leave that aside, tends to be a solution of last resort, meaning I can't solve it with workarounds. And so It started by replacing hoods and deck lids, and it wasn't just Ford, right? The other OEMs can do it. Then went to the body sides. I consider the F-150, really a breakthrough of the entire upper body being aluminum. But by the way, it's mixed material. Pickup trucks, unlike cars, use what we used to call still call body on frame, the original architecture for a vehicle. So on a pickup truck, it's a work vehicle. The frame is made from the strongest advanced high-strength steels and an aluminum body on top. So if you go back and do it from there, you're probably 20 years. But remember, a whole bunch of intermediate introductions. And now it's by far the material of choice. So at GM, I had the opportunity actually to grow R&D. We ended up opening labs around the world versus just in Warren, more than double the size. Got a 10x increase in patenting, and I will add corresponding in publications. I think there's an important message there that if you isolate yourself from the world, you lose peer review. And I actually agreed to stay in GM through the bankruptcy. If there was any part of my career I would not recommend people opt for, it's living through a bankruptcy, but we kept the tech pipe alive. My last press conference was actually the Cadillac Super Cruise. And then I said, how much time do I have left? I'm not going to say how old I am, but you look at the clock and said, if I'm going to go to university, it better be now. So I joined U of M. Long journey, but I'm finally doing what I set out to do 50 years ago. Right?
Yeah. That's right. And your research isn't even in metals.
Well, actually, when I came here, because my background on the bench had been all metal, and I started with polymer composites, but quickly moved into metals, back to my home in metals. So I still do work on castings, on sheet forming, as well as polymer composites, and now batteries. Right?
Yeah, that's fantastic.
So before we get back to the career discussion, there's a point that you brought up that I think would be worth unpacking, especially if there's any students out in the audience, which is this idea that changing materials is often the last resort. And when you have projects that are being led by, say, a mechanical engineer, they're just thinking, oh, I grabbed this thing off the shelf and it has whatever properties it has. So can you think of any particular stories or experiences that you had where it was necessary to really do some materials innovation and it wasn't just a matter of, oh, change the geometry or connect things differently?
Well, first of all, you have to recognize if you are switching a material, chances are you're now developing a new supply chain and a new expertise. So it isn't just, oh, I'm now going to have this material in the form I want, exact form I want, ready to bolt onto the vehicle, right? Whether it's a panel or a casting. And when I say it's the last resort, typically if you can develop a mechanical or electrical workaround, you can do it faster because you don't have all the new risks and certifications with a new material, right? Despite all the tests you do in product development, and I don't care if it's a phone, a car, I won't say a plane, right? You learn in the field, right? Hopefully in safe incidents, right? And so when you introduce the new material, it's giving you one of two things. Performance improvement, you can't get it any other way, or cost reduction. Both of those is you're meeting value to customer. So the message there, it's normally the challenge for materials engineering, is meeting both of those at the same time. I'm giving performance at equivalent or lower cost. And that comes through great research and engineering, right? So whether it was aluminum, Aluminum castings replaced cast iron a long time ago because it was technology understood, and the payoff was terrific weight reduction.
Right.
Better thermal management. But for those of you who don't know, the hot part of it, I'm talking about internal combustion engine, that's where the gases explode. That's where your gas and diesel ignite. That's actually a cast iron liner that's inside the aluminum castings. So I think the other message is the days of single material intensive products are over. We've learned in factories and in design how to handle multi-materials. And now, more than ever, the challenge is joining and corrosion with mixed materials. So for those of you out there thinking a materials engineering career, I'll call it job security, right? There are always new materials to invent, existing materials to improve, and mixtures of materials that, if you go back to the first cars, a roll of steel came in and some castings came into the the Ford plant, and a car popped out with some wood, right? Now, different grades of steel, different grades of aluminum, and that's in any product, whether it's your phone, your plane, or your car.
That's amazing. So when you came to Michigan, I think one of the first big projects you were tapped for was LIFT.
Yeah.
And so that was you kind of went down the rabbit hole with that.
Well, it turns out that while I was at GM, I was also on the visiting committee for NIST, the Department of Commerce National Lab, fantastic lab in Gaithersburg. And I was actually in that role, which I eventually chaired. I was also chairing what we had as the manufacturing subcommittee, in addition to looking at them. It's one of the few laboratories in the government labs that's dedicated to support industry. And whether it was modeling, whether it was materials, there was clearly a need for our R&D infrastructure in the country to improve on manufacturing. And I'm talking about the years, the 2000 decade. And so under the Obama administration, there was the call for the U.S. to develop a program that was similar to the Fraunhofers in Germany, where companies and academia in independent not-for-profit laboratories would help transition technology and develop new technology between academia and industry. And so we actually won the second of those on lightweight metals. And, it was intriguing at the time, being an East Coaster, even though I had been in Michigan by that time for a long time. I never really recognized the tension and rivalry between Ohio State and U of M that people cared. So the dean, when I first got here, had asked me would I pull together the proposal for that? And I said, let me think about it. I just got here. Went back a couple of weeks later. Yes, I want to do it around lightweight materials. But by the way, I've already called Glenn Dane over at Ohio State, and I'm going to drive down there. After he got off the floor, he said, that's up to you. So together with them and EWI, which is the Welding Institute, we founded LIFT. It's in downtown Detroit. I was really proud of the fact we were a new anchor tenant in what's called Corktown, that now is where Michigan Center, we were part of the revitalization of that part of Detroit, which was really something I'm still proud of. And it is thriving, right? And what we did is recognize there was synergy in materials technology between land, sea, and air, the machines that move people and goods in land, sea, and air. And so we had projects where we were crossing the OEMs and supply chain, and we had 12 universities involved, going from everything from friction stir welding of titanium for components for an aircraft to improving the welding process for Ingalls Shipyard down in Mississippi. So we were doing everything from small-scale castings to a 12-ton, literally we made a 12-ton top deck for a cruiser, and had shown that the welding approach that had been developed in terms of the sequence of events for automotive 30 years before made a better lower distortion ship. So really proud, and it's thriving down there. They've expanded, and by the way, doing both technology and workforce development.
Are there still people at U of M involved in that on the research side?
Yeah, Dan Cooper does some extrusion. In fact, I'm going down there because since I've been there, they've moved into casting.
Uh-huh.
And so I'm actually have a trip scheduled with my new postdoc to show them the equipment there, and we'll do some scale-up casting.
Fantastic.
That's great. And I know you have other active research areas as well. So what are some other projects that you're working on currently?
Yeah, so again, I'm working on, there's a theme in my research, because I'm working on basically nano composite materials. And I go there because not only did the rest of the field go there, but when I started my research, there were natural nanoscale materials, but we didn't have the microscopes that could see them, and we sure couldn't engineer them. So we're putting 10 nanometer ceramic particles in situ, reacted in situ in aluminum castings to increase the performance. I'm putting nanomaterials in polymers for both structural applications, for polymer composites, but I'd say as compared to industry, being an academic really gives you the flexibility to, this sounds interesting, I'm going there, right? So one of my, I had a program on adding these carbon nanotubes and graphene to carbon fiber composites to improve the properties. And I get a new graduate student, other one graduated, PhD student, starts working and it comes back to me. I'm not that interested in mechanical properties. Okay, Avi, go to the library and come back. These would be really good for EMI. Well, I had actually led the team that was working on the coatings for the engines for the stealth bomber, so it's taking me back to my physics days, sure. And we started baking the material. And here's another thing that I'd say the advantage of what I call the big industrial labs and a university like U of M. Turns out if you want to have EMI absorption is where you have electromagnetic waves. So the standard way to shield from those is you put a conducting metal cage around them. I'll say Faraday cage for those of you who are technical. But all that's doing is reflecting the wave to the next component, right? So people have wanted to absorb it. Well, a perfect conductor reflects it. A perfect insulator just transmits it. A partial conductor, where you can tailor the conductivity, can absorb it. Perfect application for polymer composites, where you put conducting materials in. And you can tailor the conductivity. So it turns out, we and others in the field, are getting there. Oh, wait a second, if you foam it, you put extra air interfaces in, so you get multiple reflections. That's better. And so we were doing it, the properties were improving. And I realized, we were doing Edisonian. Go make the foam and then go measure it. So I said, must be somebody who knows how to model this. So I found Eric Mickelson over in electrical, expert in wave mechanics. And he goes, random pores are too complicated. If you make periodic pores, metastructures, we can model it. Okay, so he taught my student how to set up the model and do it. And now we've really advanced it with some novel geometries. The figure of merit is decibel absorption. We could take a 10 decibel baseline material with a single spike peak and have it, the target is 20 decibels for and have it do it over the entire 4 gigahertz spectrum, just by tailoring the materials in the composite to get the right conductivity, and then putting the right structure of pores in, right?
So you're making metamaterials.
It is a metastructure, absolutely. Right. Where the materials inside are actually graphene, nanomaterials, and CNTs. I will tell you the most surprising thing I'm doing now, given my historical background. We were doing a project with Ford where the goal was to replace glass fiber in fiberglass with natural fibers, right? Fiberglass, making glass fiber is very energy intensive, right? The CO2 footprint is high as compared to growing a plant and taking fibers out. Right. And so our goal was, let's go increase the strength of those fibers. There are 3 plants that have you can extract strong fibers from them. Hemp, so we were interested in doing hemp. A little side story, at the time, marijuana was still illegal in Michigan. I tried explaining to our policy folks, I'm only taking the stem. I'm not doing, no, you can't bring them in the lab. The other choices were bamboo and flax. We went with flax. And the whole idea with the theme of nano, people today grow plants to remediate soil because it absorbs particles. And Professor Taub over in chem engineering had shown that you could absorb nanoparticles. Oh, geez, let's go get the plant to absorb some nanomaterial. Hopefully it will get to the fibers while they're growing and strengthen them. Well, the plants were absorbing them, but it was clogging their system and killing them. So that didn't work. And I realized, maybe we got to study how plant physiology. Now here I am learning to be a metallurgist, expanding into polymers, and now interacting on plant biology and actually, not going to put the details because we just filed a patent, actually have created a better fertilizer. So the ability to go on a breadth of activities at academia is just marvelous.
So Ron Cantor, he came up and gave a talk. He's been on our podcast. His research, he's a fiber material scientist, is with industrial hemp, because industrial hemp has no THC in it.
Right.
But it grows really fast, and it's one of the only plants that actually puts nitrogen back in the soil. And it grows quickly enough that you can grow a crop of that, use it as your fertilizer, and then the farmer can grow corn or something else for the second half of the season, and you have this amazing fiber.
The beauty of, particularly if you're doing research on flax versus the other two, flax fibers are the source of linen. So there's been deep technical research on flax fiber in Europe that we've been taking advantage of. But at this point, we think we're making some of the strongest fibers in the world.
Separating the linen from the cellulose.
The cellulose from the, it's you basically weaken the interface by extracting some of the lignin. We're getting a little too detailed. And by the way, 6 years ago, I wouldn't even know what those terms meant, right?
Well, I only know because I talked to Ron, and we were going to try using an ultra-fast laser to weaken some of those bonds, but we never got around to it.
Well, maybe we have to give it a shot. Right?
Yeah.
No pun intended.
But the point about developing the technical expertise like you're bringing up, of course, the continuing education, always discovering new things, but it really demonstrates that you have to have deep technical knowledge if you're going to be an effective leader for technical people. So what's been your experience on the leadership journey of coming from a physics background, becoming a leader in industry and now directing research programs? How have you found that how have you found that your education did or did not prepare you for that? And what's your advice for people who might want to go into technical leadership?
Well, first of all, you said something that I wholeheartedly believe is deep technical people should be the leaders of technical people, right? Whether you're an experienced engineer, researcher, if you haven't done what you're leading the people to do, particularly on the research side, right? On engineering, look what I did. I was given a vehicle program. It's a little different, but on research, there's a non-quantifiable, I still call it the gut feel, about which projects have potential. You know, you're doing the rough idea at the beginning. What's my payoff? What's my risk? What's my investment? And by the way, I've made some bad calls in my day, but fortunately, a majority of them correct. Meaning it didn't pan out, and it didn't pan out for the wrong reason, not the right reason. But I'll also add that there are some people who are born to be leaders. I will be the first one to say I'm not one of them, right? Myers-Briggs, I'm the classic I, introvert, right? That fortunately, my first company I was in was GE, which had its own management school. You know, it was set up to select and groom leaders. And you can be taught some of the skills, whether it's dealing with people, budgets, you know, strategy. And as you go through that, the real question is it satisfying, right? I mean, most people, if you've been an accomplished engineer, you might be able to take it on and learn it. It's the question of whether it gives you satisfaction. So I remember when I was debating, finally agreeing to do my first level job, the best advice I got, which I tell, you know, I mentor a lot of students here, is as a people leader, even if it's technical, what I call the personal highs will be higher than, you know, your ability to impact is highly leveraged, right? So your accomplishment high is higher than you'll have as an individual contributor. But the lows are lower. You know, it's one thing to say my experiment didn't work. It's another one to have to deal with a bad employee or financial stress. And what you have to find out is, well, if highs are higher and lows are lower, where's the mean, right? And it's worth trying. Right? I'll add one other part. It was intriguing. I was the leaders of R&D. There was basically the equivalent of a technical society. You know, we're all technical people, so instead of going to the technical societies, this forum was created. We go to twice a year. I was always amazed in companies that are basically doing mechanical and electrical and now software products. The number of R&D and CTOs leaders that are materials and chemical background. There's something about our field, which is changing now that we have models and some more quantitative, that it is a more qualitative field where the options aren't always as clear. And I think we're trained to think more holistically. Meaning when we get a problem in materials, there isn't, go take this code, model it, and you have the answer. You know, we're still in the early stages of having real models you can count on and the approach predefined.
Coming from the physics background, you know, physics trains you, you write the equation, you solve the equation, there's your answer.
Yeah, but I was applied physics was really our way of saying materials science, right? It was Harvard.
But you know, I see, I'll never forget going to one of your lift pitch meetings. We had some stupid ideas, but what I really enjoyed was watching you during those meetings, because people would propose things, and you had over your years, and just look at your career you just described, you've gone from one area to another area to biology. You're a very fast learner, and you have really excelled at being able to rapidly bring yourself up to speed using all of those research skills you learned a long time ago. Because that's what research is. We're all a bunch of idiots. We come up with these crazy fairy tales, but we make really good fairy tales. And then we're open to the fact that we might be very wrong about these ideas, and that's okay. Because if you don't push it, you're never going to develop stuff. But because you worked as the director of a research lab, you have had thousands of hours of people pitching ideas, and you had to make these decisions. And I got to see that in that one meeting. And I won't say his name, but somebody said something, and you just said, we tried that 30 years ago, and it didn't work then, and it's not going to work now. And this is why. Because you just have a vast breadth of experience, but if you drill it all down to its very core, it's probably something you learned as an undergraduate, when you learned something as general as physics. And what are the materials concepts? They're all physics concepts. And more importantly, you probably learned in graduate school how to do research. And it's what we do as academics, I think the part that's the most satisfying thing for us in academics. We live vicariously through the success of our PhDs. And we watch our PhDs evolve, and you try to explain to them, I know you read that paper, and I know what that paper says, but I'm sorry, you just have to have a healthy disrespect for the literature. It's important to read, but you got to get out there and do the experiments yourself, because you might be wildly surprised. And that's something that takes a long time to learn, and I saw that in you. You do it so much better than I do it, but it was so much fun to watch you, and I've only seen that a few times. When I was at Bell Labs, I was lucky enough to be with guys like Bob Dines, who was the head of this division. Man, he was so good at that. And Kumar Patel, who was the head of Area 15, he was and a lot of the department heads. So, my department head was Len Feldman. I had read all his books as a graduate student. What an amazing guy. And John Pote. And all these people, they all had that ability to rapidly come up to speed, to ask the right questions, and then to interpret the results as best they could. They weren't always right. But I think that's the essence of what I see your success is based on. And what a great place for you to be now to teach students like Avi, who we had on our podcast a few weeks ago, and it was great. He's doing really crazy stuff.
Actually, I just saw him at TMS. So thank you I'll take as a compliment.
Yeah, it is a compliment.
But let me also, and I do think it's a skill I've honed, because when you're making those investment decisions at the early exploratory stage, right, you have to apply the gut feel, right? And it comes from experience. Let me give you the counterpoint to that. If you go and look at, and I'll stick with materials, and you look at breakthroughs in fields, a field will sort of die down and reemerge about 25 to 30 years later.
Right.
And all of a sudden there's another breakthrough, and it's going through that new asymptotic growth. What's the factor there? The experienced person who said, "No, we tried that and it didn't work," isn't there to discourage that new idea. So it's a dual-edged sword. And now that time constant is shrinking in, say, in electronic materials, right? But if you look sort of at structural materials, go take a look. The field reemerges about every 20 years, right? When the person who was there to say, "Oh, we tried that," or "I know better," isn't there anymore. And the young Turk can go in and do it anyway.
But, in things that are more than 20 years old, new things have happened. Our characterization tools are so much more improved now that, like you even said, we use perlite forever. That's a nanomaterial.
Yep.
But we didn't realize it. And we only look down to one scale, and then there's all these little particles that are all around that. And, They all matter.
I tell you, our field, if you look at how materials science has changed, until recently with the breakthrough in some modelings, whether it's DFT, it was the invention of a new characterization technique.
Yes.
I mean, go back to dislocations. They were hypothesized,
Yeah.
and only when the TEMs were invented, and those early ones, trust me, nothing like going to our materials characterization center today, you fib it. We had to learn how to electropolish, get it on the grid. Those were intriguing days. Fortunately, by the time I got there, they realized they had to shield your eyes from the X-rays. So there was a generation of the early microscopists who all got cataracts. But it's really that combination today of we're characterizing at the atomic level, right? And modeling in multi-scale. The advantages today's researchers have.
It's amazing.
And it's why the fields now can move so fast, right? It's a great time to be in materials science, right?
It really is. And it was great hearing Anil Sachdev talk about the breakthroughs he made with EBSD and in situ straining. And I'm sitting there 2 seats away from Ashwin. I'm like, can't you do this with nano CT better at a synchrotron? And I ask him, he goes, oh, absolutely. But I don't know if you can get down to the same scale. Well, but you can come close.
I mentioned we're working on the nano composites on aluminum. When Professor Shahani joined from Northwestern, I teamed up with him. I no longer trust 2D metallography. Right. He has we co-advise students. They go down to the beamline, and 3D tomography is just great.
Right. And they're getting it to smaller and smaller volumes, and that's the big breakthrough. Yeah. So it's just what an exciting time, and that's great.
Yeah. There's another thread there to pick up. It's not a flax thread, but we're talking about how this field we do more holistic thinking, we do more qualitative analysis, and this is part of what makes materials science special. But you're also illustrating that we're a very interdisciplinary field. And I think that's also part of what equips materials scientists to be effective technical leaders, because they have that very broad foundation to be able to acquire knowledge in this or that domain area to engage with the experts effectively. And this is something that I'm always really trying to encourage students to do, is be an interesting person. If you become an extremely narrow expert in one thing, you're probably not going to have a big impact. But if you gain this ability to talk to different kinds of people on different technical topics and benefit from their expertise, then you can really go places with that.
Yeah, and we are in a continuous learning environment. Advice I have for students, be they undergrads or grad students, take courses outside of your department.
Absolutely.
The days of the lone wolf eureka are now very rare, right? When we're going after a problem, it tends to always require a multidisciplinary team. And you should at least understand when one of your colleagues from a different department is telling you what they're doing and what their results are. At least have the basics of mechanics, the basics of chemistry, the basics of thermal management, because those tools and those capabilities combined with yours, is what leads to the breakthroughs now. Right? And as a student, you have a unique opportunity to take electives, right? Once you get into work, you get focused, you'll be put on interdisciplinary teams, but you get very busy. And then you get a life with that gets in the way of outside work. Your time as a student, take electives. Take more courses than you're required to take, but take them outside of your discipline. It's something, when I was at Brown, It was the one school that had no required curriculum. You can make your own curriculum. If I made a mistake, I mean, it was great. I loved it. I learned a lot. I took too many material courses. Given my career, I didn't take a single economics course. I was very focused, and fortunately, I learned it over time, but I always encourage my students to take other classes.
Mm-hmm. So now you're doing something completely different. Well, maybe not completely, but you're running this new EV center.
Yeah.
Can you talk a little bit about the EV center, what you're doing, and what are the challenges and the opportunities?
Yeah, I'd almost call it a once-in-a-lifetime opportunity. The university, and it was in place before I got here, had developed a pilot line to make battery cells. It is 98, in addition to that battery lab running some of the labs for the faculty, this pilot line is 98% used by industry. And it was done together with Ford and the state. Ford had decided originally, instead of putting it in their lab in Dearborn, they put it here with support from the university and the state, serving dozens of companies every year. Well, the equipment was, our customers were saying they wanted what's called the wider format, a larger battery. And, faster run times, et cetera. So it was time to upgrade. I always tend to think big dollars, so I went to the state together with Greg Less, our director, for $12 million just to upgrade it. Fortunately, our public affairs people got involved. Together with the dean's office, they saw an opportunity. We got a $130 million grant from the state.
Order of magnitude improvement.
And $20 million from the university. But the charter from the state was intriguing. Almost half of theirs was go improve your facilities, right? Beyond just the pilot line. We're actually doing a new building. We're upgrading what used to be the engine and transmission dyno labs now to handle battery propulsion. But there was $20 million to work with companies on workforce and $50 million on technology. Wow. And the state of Michigan relies on the economic development that's associated with automotive. So the charter was see what we could do to support the companies in Michigan and coming to Michigan through that transition from gasoline engines to battery electric vehicles. So we created something that's relatively unique. We decided, given that charter, not to do what I call, and with all due respect, I've been involved in my industrial life in academic consortiums, but the typical one, they have a membership fee. You come in at the beginning of the year, you hear what they did last year, you give them guidance on what projects to do, you come back a year later and you see the results. The way we set this up, the companies actually truly decide the projects, but a vote on a project means I'm going to work on the project. So these are truly collaborations where the industry people are working with the faculty and the students on every project. We thought we'd have it, I made it a minimum of 3 companies on every project. Most have 5 or 6.
Wow.
And they've now been underway enough. We're actually getting patents, we're getting papers, and we're looking at everything from improved batteries to improved motors to thermal management. And I thought originally we were going to stay on vehicle. Then the companies, and my personal belief is the grid's not ready, so we're working on improved charging in the grid. It's really, for some faculty, their experience working with companies. I think one of the biggest impact we've had is getting particularly some of the newer faculty comfortable working on a company-directed, company-collaborative project. And it's really the chance to see your stuff implemented. Right? We're producing the papers, we're producing the patents, but the goal of every project is to have it commercialized, right? So we just finished year 3. The dean's office is happy, the companies are happy. We have over 20 companies. We just had our 2nd annual symposium. almost 400 attendees and only half from outside the university. I mean, I'm feeling really good about the contribution we're making to this transition.
But you mentioned it's more than just cars. It's what other areas are?
So we launched focused on light vehicles moving to battery electric. And by the way, the industry is well on its way to where, unsubsidized by the government, you will have not only a better mobility experience. I don't miss going to the gas station. I pull in at night, plug my car in. I remember I realized I had my first EV. This is after I left GM for 12 months. Hadn't done a thing.
Right.
Called up the dealer, what am I supposed to do? Rotate the tire. I didn't believe him, so I called the chief engineer back at GM. Rotate the tires now, and at 24 months, rotate them again.
Yeah.
It cost me $1 per gallon equivalent. So it's a better mobility experience, but we are well on our way in the near term, meaning in the next 4 to 5 years, where your cost of ownership of a BEV will be lower than that of an internal combustion engine vehicle. And that's through the technology development. Right. So helping that journey is really rewarding.
Plugging in at night, not going to the gas station. I calculated I save 24 hours, 2 days of being awake. I recoup every year because I'm not going to the gas station. Because I'm cheap, I go to Costco, so I have to drive to Costco.
Oh, you wait in line, yeah.
And then I have to wait in line. It's horrible. And I recoup 2 days of my life because it's so easy to just plug it in my garage.
Yeah. So with that part of our portfolio well in hand, again, we have over 20 companies heavily involved. We're now moving into the other electrified mobility areas. Actually first now moving into drones. Just, right. Reviewed with our advisory committee, they've done it. If you think about the powertrain of a boat, a drone, a car, it's batteries, motors, thermal management, right, and charging. Yeah. So the overlap in technology is there, and now with both the explosion of applications of drones, and we're doing that, do that with MR at university, but the need to ramp up overnight domestic drone manufacturing. A lot of the supply chain is our existing supply chain in Michigan. Right? It's composites, it's batteries, it's motors. So, we're trying to help incentivize that.
And the whole robotics explosion.
Yep.
Same thing.
We can talk about AI too and how it impacts materials, but I don't know that that's this focus.
So the EV Center is far more than just coming up with better cathodes and anodes and electrolytes.
Yeah, if you look at what it takes, you need energy storage. The energy storage is the battery. You need to get electrons to the battery, so it's the grid to the transformer to the charging station. Then the electrons have to make their way to the motors. And for those of you familiar with the internal combustion engine vehicle, it's had the problem but the luxury of operating at high temperature gases. And, well, if this is engineers watching, Carnot efficiency, the higher the temperature difference between ambient and that, the easier it is to get heat transfer. Batteries and motors operate at much lower temperatures, and so the thermal management is more challenging. If you look at today's vehicles, it's still sort of a Rube Goldberg of the motors want to be at this temperature and the batteries at this, and it's probably the area that's seen the lowest level of improvement and is actually a large part of our portfolio. So it's everything from batteries, motors, power electronics, and then charging. And a lot of pull on end of life, right? Because it takes a lot of energy to create the battery.
Sure.
And it's intriguing. When the battery has only degraded about 20, 25%, still a pretty good battery, it can no longer accelerate the vehicle fast enough. So I have this basically still functioning battery that I can either treat like material from the ground and collect the elements, or find a secondary use. So
I'll take it on my solar array.
and if it wasn't for a different point on the energy power curve, right?
Right.
So we're trying to see, will it make sense for grid use? Will it make for that? And this whole challenge now of, we benefit on the cost of ownership of electric vehicle because you charge it off peak. I started my career at GE. My first thing was distribution transformers. I'm back to the future on that. It turns out the electron production capacity is set to meet peak demand on an afternoon in August. Right. A lot of the time, those electron generators are turned off. Yeah. And so it's almost free electrons in terms of capital investment if you charge at night. And so it's really the grid that distributes it. That's the new challenge. And now not only electric vehicles, but we're competing with data centers. So
that's right.
Great time.
A personal curiosity question. You mentioned light vehicles, drones. You didn't talk about heavy vehicles, freight, things like that. And I see some efforts out in the world to electrify, even on campus, our campus blue bus, they have electric ones now. And I've just always been very skeptical of that from a scaling point of view in terms of mass, power, volume, these sorts of physical constraints. So what's the deal?
So it depends on, and actually not so much the size of the vehicle, but its use cycle. The beauty of, one of the advantages of a battery electric vehicle is today, you burn this fuel. A small fraction of it actually gets to move the wheels. And then when you want to stop, you take friction materials against your brake rotors and turn it into heat. Right? So, by the way, less than 20% of the energy in the fuel actually gets to the wheels. A third of that moves the air around. A third of it heats up the tires and the pavement. So you're down to less than 10% actually turning into kinetic energy. When you have either a hybrid or motors driving, you can run the motor in reverse, called regenerative braking. So I can recharge the batteries by slowing down the vehicle. So for something like a garbage truck, a school bus, which makes many stops, you take energy to get it going, but then you can recover a substantial portion when it stops. I think the real challenge is going to be long-haul trucking. And, that's being debated now. Should I use biodiesel? Should I use hydrogen fuel cell? Or should I use batteries? You can make it so that the tractor can have the range you need. The challenge is the time it takes to recharge it, because it's a lot of energy. And so in today's world, where there are restrictions on a human driver, there's time to park it because they legally have to. We're well on our way to a world of fully autonomous. Those trucks are going to run 24/7. So how are they going to handle the downtime of charging? So I personally believe, having supported in my GM time both fuel cell and battery electric, we weren't sure which would work for light vehicle, and invested in both. I think for light vehicles, the battery electric has won. I think for other applications, whether it's marine, heavy truck, there's still a race going on.
It's interesting. I read a story. I don't know if this is apocryphal, but it certainly, from a physics point of view, could be true. I heard that one of the world's largest and heaviest trucks, a monster dump truck, they made it an electric vehicle. And it only had to be charged once. And it never had to be charged again. Because all this truck did was drive up this mountain to a strip mine. Drove up empty. It got loaded with all these rocks and charged on the way down.
Something sounding like a perpetual motion machine. So
But
I
it's
need
not.
to see. I need to see the. I understand now in theory, but I'd love to see the actual result.
Well, it's
It would be a very good engineering assignment. I bet you it gets charged somewhere along the line again.
Well, it all
There
gets
are still
charged.
parasitic losses, but no,
Right.
it's a nice model.
But the energy to mine the rock and put the rock in the truck is where it's not a perpetual.
No, I understand how the cycle might work, but we'll see. The breakthroughs that we're getting, look, economic growth is, in the world we've been in, tied to energy usage. You can plot GDP and the amount of energy used, and they scale, right? And so the emissions problems are an issue, right? Whether it's climate change, whether it's local, NOx and SOx issues, on diesel, particulate, and we've been working on ways to improve that in burning fuel. And remember, creating an electron, if you're starting with petroleum, you've got to capture the emission somewhere. It's just easier to do it at a central source than at a tailpipe. The more we develop electrified products, the greater the diversity of fuels, the easier to manage the things, and at the same time, the more vulnerable we get to grid problems, right? But it's more efficient use of energy, and we'll be going more and more into other products, which is why we launched as the Electric Vehicle Center. We're now going into other mobility products, but go in not just your car, go in your house and realize how many motors are in your house. Doing the things you're now too lazy to do. Mm-hmm. What's opening and closing your garage door? Do you go out of your car, unlock it, and lift it up?
Only when the power's out.
What do you think's in your refrigerator? What do you think is in your microwave fan?
And now that my wife wants it, what do you think's in my blinds, opening and closing them? Boy, is that expensive.
And for the materials engineers and scientists, it's new materials that produce the electricity, move the electricity, use the electricity, right? And the rate at which technology is changing, for the students out there, you're entering the field at a marvelous time. I mean, I'm ancient, right? My grandchildren refer to me as, that's so 20th century, right? So 1900s. The pace at which new materials and products are being introduced is such an opportunity, right? To really make a difference, right? Whether it's sustainability, better performance, just a better life. Go for it, right? We need you.
All right.
All right. Well, thank everybody for tuning in, and thank you, Alan. That was fantastic. And so we hope you tune in to another episode of Undercooled. Thank you.
Great. Thanks,
See you
everyone.
later.